So stay on such an angle. I don't get it. Like no matter what I do, I can't win. Still on that angle. How would that be? Strange. This could seriously take me like 10, 15 minutes. Yeah, but I want it to be as big as possible so you guys can read it. I know why it's slanted. I've tried everything to make it not slanted. I mean, besides this, what could be making it slanted? I don't. I did that. I don't know. Okay, anyway. Is that good? Okay. All right, so we're going to start out with something you really already know, and that's some more U-substitution. So here it goes. Ready? Okay, so right now you don't know how to integrate tangent. I mean, you could integrate other type trig functions, but right now you don't have any way to do that. So if you get creative and write tangent as sine over cosine, and then, by the way, can I move the sine off to the side, guys? Can I? So the sign that's on top can be moved off to the side. Okay, so I'm just playing around with it. Now watch what happens. Because you have a fraction, let's let u be the denominator, okay, and see what happens. We're going to try U substitution here, see if that works. And so if I let u be the denominator, what's the derivative of cosine, guys? Negative sine, and then you can multiply both sides by dx to get to there, and you can multiply both sides by a negative to get to there. Okay, and so after playing around with that off to the side, you can now go back to your original problem and start substituting. So what can I replace this with, guys? And replace that with what now? 1 over u. And what can I replace sine x dx with? Negative du. And then I can pull the negative out if I want, right, to get to there. And then from there, what's the antiderivative? 1 over u du, guys. What is it? Yeah, it's ln, absolute value of u, plus c. And then at the end, don't forget to put your u back in. Okay? So there's my answer. Okay, so by replacing tangent with sine over cosine, playing around with it, doing a U substitution, and end up being something I could go ahead and integrate, right? Okay, so get another one. Again, notice, you don't know how to integrate that, do you? I mean, you might be able to integrate e to the u, or e to the x, or e to the t, right? So if the exponent's a single variable, you have a chance to at least integrate that, right? But you can't integrate e to the x squared, can you? So doesn't that kind of force you into letting u be the exponent on something like that, doesn't it? So that's what I did. And so if I let u be the x squared, okay? And then what's the derivative of that with respect to x, guys? What is it? 2x. And then you play around with it by multiplying both sides by dx, and multiply both sides by a half. Okay, and then let's see what happens when I start substituting back in. So going back to the original problem, which, by the way, here was the original problem. Notice what I did. I moved the x over here next to the dx. Is that okay with you guys? Okay, so I took the original problem and I moved the x next to the dx. Okay, but anyway. All right, so now I'm here. Okay, and so what I can do now is I can replace this with what? E to the u. I can replace that with what? What can I replace x dx with, guys? 1/2 du. Okay. And then from there I can pull out the half, and then notice. By the way, I know what mistake you're going to make if you're not careful. You cannot integrate unless you have e to the u du. You cannot have e to the u dx That's the mistake you guys are going to make. You're going to forget to replace the dx, and it's going to look like it works, and what you get is not going to be correct. So you're not ready to integrate until it's e to the u du. Is that clear? You cannot have e to the u dx. All right, guys? Yeah. All right. So once you have that, what is the antiderivative of e to the u du, guys? What is it? E to the u. And then don't forget your plus c. And then at the end, don't forget to put your u back in. So if you replace u with x squared, you get your final answer there. Okay? Good? Next one. Okay, again, you have a composition. So what do you typically try if you're going to try u substitution with a composition? You're going to let u be the what? Inside. The inside of the composition. What's the derivative of that? 2. And then if you multiply both sides by dx, you get that. If you multiply both sides by a half, you get that. Okay, so now that I solve for dx, I can replace dx with what? 1/2 du. And what can I replace all of that with, guys? All of that becomes what? Square root of u, right? Then you can, if you want, you can pull out the half. Okay, so you get this, and then pull out the half, and continue on the next page because I ran out of room. Okay? Okay, so just picking up there, in order to integrate that, shouldn't I write it as u to the half so I can use the power rule for integrals? Yes? Yes. With me? Yes? You sure? Mary, you got something there or no? No? You sure? All right, okay. So by adding one to the exponent, dividing by my new exponent, I get to here. Okay, and then if I want, I can invert that into a 2/3, and then this becomes square root of u cubed. Okay, everybody with me on this? And by the way, square root of u cubed turns into what? Square root of u cubed is the same as what? U square root of u. Okay, so this is where we're at, right? Okay, so once we get down to here, we have two choices. Okay, the way we would normally finish this from here is we'd do what? We would replace the u with what? We'd replace the u with what? Yeah, 2x plus 1. And then from there, stick in your upper limit of 4, and then subtract what you give, and you stick in your lower limit of 0. And so if you do that, you get this. And if you simplify that, you get this or this. Okay, so that's one way to finish it. There's nothing new there at all. After you do the u substitution, don't forget to put your u back in, and then finish the definite integral by plugging in the upper limit of 4 and subtracting what you get when you plug in the lower limit of 0. Okay, guys? Are you following me? All right, now here's what's new for today. Here's what's different. Instead of doing it that way, there's another option. What is it? It's called what? Change of limits. So instead of putting the u back in, you see how I replaced u with 2x plus 1? Instead of doing that, this is what you could do. Ready? Just take that formula and put the 4 into there. So if I put the 4 into there, what do I get? Quick. 9. If I put the 0 into there, what do I get? If I put a 0 there, what do I get? 1, right? Okay. All right, so by doing that, notice I change the limits from 0 to 4 to what? 1 to what? 9. And so by changing the limits, all it does is makes the rest of this a little bit less messy. So when I change the limits, I don't have to replace the u anymore, do I? I can just leave it as u, right? Does that make sense? Yes? And then so I just replace u with 9 and subtract what I get when I replace u with 1. I mean, essentially the same thing if you think about it, but basically it just saves a little bit of work. That's all it really does. Is that clear? Yes? Yep. Okay. So just remember, guys, the reason you had to put the u back in there is because the 4 and 0 were x values, weren't they? They were in there at the beginning when everything was x. So if you're going to leave the 4 and the 0, you better replace u with this before you continue. Now, if you change the limits, then you can just leave u as u without replacing it with anything. Does that make sense? But you're going to do one or the other. The mistake you're going to make is you're going to mix the two methods up. And then you're going to get incorrect answers. You're not going to do that, are you? No. Either do it this way or do it this way. All right, one or the other. Okay. By the way, and again, you're probably wondering, well, how do these turn out to be the same? Well, you can probably see it algebraically, but graphically, let me explain. This was the original problem, right? When the function was y equals square root of 2x plus 1, going from x equals 0 to x equals 4, correct? Once you change the limits technically and left the u in there and change the limits, now you're going to have the graph of y equals this, aren't you? From what? From 1 to what? 9. So clearly they're going to be two totally different looking regions, aren't they? But they have the same area. Is that clear? Yes? Okay. All right, good. All right, so just keep that in mind. Okay. Yeah. All right, why don't you guys go ahead and try one. Go ahead and try this. And again, I gave you a hint on what to let u equal. Because remember, anytime you have a fraction, typically you let either u be the whole denominator or the inside of the denominator. So on this, let me just have you try letting u be the whole denominator and see what happens from there. Okay, so everybody give it a shot. So Gravier's absent. And Michael. Yeah, put that away. I'm going to have a nice new phone otherwise. I could actually use a new phone. I still have one of those old slide phones. Please don't forget how to do the chain rule on this when you're working off to the side there. Do anything. I don't know why it's doing that. All right, well, you can keep working. I'm going to catch up to where you guys are probably at. So if I let u be the whole denominator, I think it'd be better to write it like that since it is a composition. So I'm going to have to use a chain rule, right, to take the derivative to get du over dx. So using the chain rule, that's the derivative of the outside. Put the inside back in the way it was, and then multiply by the derivative of the inside, which is 3. Okay, so I end up with this. Okay. And then if you multiply both sides by dx, you're going to get this. Okay. And then if you multiply both sides by 2/3, you're going to get this. And if you're wondering why I did this, by the way, you could have solved for dx. That would have worked out fine. But the bottom line is, I stop there because now if I come over to here, I get this. And if you don't mind, I'll move the x off to the side here. Okay. Bless you. Now, remember, you're trying to get these to match as much as possible. So you might have to play around with this a little bit. You might have to play around with this a little bit to get as much of it to match as you can. And so where I stopped, I can now replace all of that with that, can I? Yes? Everybody agree? So that becomes 2/3 du. Okay, now I have a problem, don't I? What's the problem? Well, first of all, I can pull the 2/3 out. That's not a big deal. But what's the problem here, guys? Yeah, I still have an x. I cannot have a mixture of x's and u's. It's got to be all u's, du's at this point, doesn't it, before I can integrate? Right? Everybody agree that this is not good? Okay, so don't I got to come over here and maybe borrow something from here to help me solve this for x? Everybody agree with that? So that's what I'm going to do. So I'm going to take this and say, okay, if u equals that, I can solve this for x, right? By squaring both sides, and then subtract 1 from both sides, and then divide both sides by 3. Okay? And so now I can replace x with this, can I? Everybody see what I'm doing? Okay? All right, and so making all those substitutions, I can replace x now with u squared minus 1 over 3. And if I'd like to, I can pull that 3 out, right? Okay. All right, and then I can go ahead and integrate, right? Everybody agree at this point I'm okay to go ahead and integrate? Everybody okay with this now? To go ahead and integrate? Okay, so obviously it's u to the 3rd over 3 minus u from 1 to 5. Okay, and then I guess what I'm saying at this point is I know you're probably out of room, but I've got 2 choices to finish it now, right? I can either replace u with this, right? I can either replace u with that and then continue, or I can change the limits. Everybody agree I can change the limits instead if I want? It'll just make it a little bit less messy. So here's what I'm going to do. Instead of replacing the u here with the square root of 3x plus 1, I'm going to leave it as u, but then I'm going to change the limit. So, okay, so how about the upper limit? How about the upper limit? The old upper limit was what? X equals what? 5. And so using the fact that u equals the square root of 3x plus 5, what do I get? Don't I get square root of 16, which is 4? Yes, that's my new upper limit. Okay. Anybody agree? That's my new upper limit. And then my lower limit, which was what? What was my old lower limit? What was it? Come on, guys. 1. And so using the formula u equals 3x plus 1, I'm going to put in the 1 there. And what do you get? Square root of 4, which is what? 2. Okay, so that becomes my new lower limit. And so by changing the limits, I can make the rest of this a lot less messy, can I? Yes? Okay, and so from there, how do I finish, guys? You tell me. How do I finish this now? What do I do? Come on. What do I do? what do? Yeah, substitute in the 4 and subtract what I get when I substitute in the 2. Isn't that proper procedure from here? Okay, so let's do it. So what do you get when you put in a 4? 64 thirds minus 4 minus what? 8 thirds minus 2? Yes? And so what do you get? Let's see. 64 thirds minus 4 minus 8 thirds plus 2, which is, what, 56 thirds minus 2, right? Which is 56 thirds minus 6 thirds. Is that right or not? Okay, and then so it's what, 2 9s times what, 50 thirds? Which is 100 over 27. Okay? Make sense? Okay, so that's, I know it's pretty long, but actually it might have been a little bit uglier if you didn't change the limits. So that's definitely one where you'd want to consider changing the limits. Again, you didn't have to. You didn't have to change the limits, but this is an example where you see it does make it at least a little bit easier. Okay? Okay? So I guess you really never have to do a change of limits except on certain AP questions where they design the problem to force you to use it. Okay, and so that's what I'm going to show you next. This is an old AP question. Okay, so example 5 is, again, similar to something I saw in an old AP exam. All right, so let's look at it. All right, now, again, you've never seen a problem like this before. However, the fact that this is a, first of all, what is that? What kind of function is that? It's composition. And so what do you know about compositions? You typically need to what? Use U-substitution, don't you, to integrate a composition? So doesn't that give you one hint right there just by giving you a composition inside the integral? So what are you going to do off to the side? Let U equal what? The inside of the composition? Isn't that what you typically do? So let U be the inside, which is 2x. And what's the derivative of that with respect to x, guys? What is it? 2. And then if you play around with it, you get this, right? Okay or not? Okay? All right, so at this point I replace dx with that. And then I can replace this with what? F of u, right? All right, now. And you can pull out the half, can't you? Oops, sorry, that's du. All right. Now, you guys, you're not going to want to put u back in at this point because then you're going to go right back to where you started, aren't you? Right? So you don't want to put u back in. The bottom line is, for example, if you're punching this into your calculator and you use x instead of u, would the calculator give you the same answer either way? Would it? Yeah. So at this point, once you, oh, let me take that back. Let me take that back. If you're going to leave u in here and punch it in your calculator, then you're going to have to do what to the limits? Change the limits. Okay, so let's do that. Okay, and so using u equals 2x, and if I put a 3 in there, what does my new upper limit become, guys? 6. And if I put a 1 in there, what's my new lower limit become? 2. So everybody agree if I'm going to leave u in there and never go back to x, I'm going to have to change the limits and go from 2 to 6? Okay. All right, now notice that you really don't need to integrate because all the answers still have an integral in there. So you're not going to need to integrate anything, are you? No. What you're doing is just trying to play around with it and get it to match one of these answers. Now, as I was saying, At this point, since you're never going to go back to being x again, does it really matter if this is a u or an x, or does it really matter what it is? You can call it any variable you want, right? It really won't matter at this point if you never go back to the old limits. And so, is this one of the answers or not? It is. Which one? D. Okay, makes sense? Okay, so at this point, it really doesn't matter if it's u or x or t, whatever you want to use for the variable. It really doesn't matter, because if you're punching that in your calculator, it wouldn't know the difference between x and u anyway, would it? Okay. So again, that's an often old AP exam. So even though I said a few minutes ago that changing limits is optional, on something like this, clearly it's not optional, right? They're forcing you to know the concept of change of limits, aren't they? In order to pick out the right answer. You understand? Okay? All right. But on any other, general problem, when you do U-substitution, changing limits is nothing more than an option. You don't have to do it unless it's something like this. Okay, last page. All right, let's go back to symmetry. We did a little bit of this at the beginning of the year when I was reviewing, if you remember. And so, think about it. If you replace x with negative x and you get the opposite y values back, then the function is odd. In other words, it has origin symmetry. If you replace x with negative x, play around with it, and you get the same function back again. In other words, you get the same y value that you would have originally if it was just x. Then think about that. That would be y-axis symmetry, or even, right? Think about that. Okay. In other words, suppose you put in a 2, and you get, I don't know, suppose this is 3, right? What do you get when you put in negative 2, guys? You get what for the y value? What do you get? Negative 3. So the bottom line is when you replace x with negative x, and you get the opposite y value back, right? You get the opposite of what you started with for the y value, then that's what type of symmetry? What type of symmetry does this look like to you? Yeah, it is odd, so it's what? It's an odd function, so it has what type of symmetry? Origin symmetry. You understand? Yeah? All right, let's look at the other situation. Okay, suppose that's my graph, okay? And suppose I put in like 2 and I get, I don't know, 3 here. What do you get for the y value when you plug in negative 2? You get what? 3 again. So the bottom line is, if you replace x with negative x, right, and you get the same y value back, that means it has what type of symmetry? Y-axis. In other words, what type of a function? Even. Okay, so if you think about it, you really don't need to memorize what's going on here, right? It's just common sense, isn't it? Can someone get the door for me? Thank you. So with that in mind, then, all that does is just helps you understand these two things. That's all it really does. Then now there's something else you got to remember here. Doesn't the graph of sine have origin symmetry if you think about what it looks like? Yes? And so when you replace x with negative x in sine, you'll get the what? The opposite y value back? Yes? And doesn't cosine graph have y-axis symmetry, doesn't it? If you don't believe me, just draw a rough sketch. Okay, cosine looks like this. Cosine of 0 is 1, right? Cosine of pi over 2 is 0. Cosine of pi is negative 1. And so on, right? Yes? And so isn't this what it looks like, guys? Isn't it? What kind of symmetry does that have? Yeah, well, it has y-axis symmetry, so it's even. Yes? Okay, and you could do the same thing with sine if you're not sure. So the bottom line is cosine has y-axis symmetry, so if you replace x with negative x, you're going to get the same y value back, right? In other words, you're going to get the same function back. Okay, so with that in mind, let's do a couple examples and we'll be done. Okay. All right, so what does this have to do with integrals? Well, that's where I'm going next. Okay, so this is kind of stuff that you learned in pre-calc. This is nothing new. Now I'm going to turn this into something new by looking at the following. Suppose f is odd. In other words, it has origin symmetry. So for example, suppose the graph of the function looks like this. Okay, there's the function. Right? Doesn't that function have origin symmetry? Yes or no? Okay, and so what happens if you integrate something like that from negative a to positive a? What if the upper and lower limit are the same? Isn't the positive and negative area going to always add up to 0? They're going to cancel each other out. So without doing any math, you know that's going to be what? 0. So the bottom line is, if you ever, on an AP exam or on the homework tonight or on my next test, if you see an integral that has, opposites for the upper and lower limit, it might be worth your time to at least think about whether that function has any type of symmetry. So in this case, since that function does have origin symmetry, without even integrating, I know it's going to be what? 0. Is that clear? Yes? Okay. Now, how would that change something like this if a function was even? In other words, if it had y-axis symmetry. So do you agree that this is an even function, this parabola right here? Yeah, because it has y-axis symmetry. What happens in this case when you integrate from negative a to a? Well, they don't add up to 0, but you get two identical areas, don't you? So what you can do to make things easier is, instead of integrating from negative a to a, which might require a lot of algebra, as you saw in that example a few minutes ago, instead of doing it that way, can't you just integrate from 0 to a to get that area, and then just double your answer by multiplying by 2? Wouldn't that make it a little bit easier? Yes? Okay? All right, so this one's really easy because you don't have to do any integrating. This one makes things a little bit easier, but you still have to integrate. But it's easier to integrate and put a 0 in than it is to put in a negative number. Okay, so again, knowing this makes the problem a little bit easier. Knowing this makes the problem a lot easier. Okay? Okay, 2 more and we're done. Ready? All right. So what do you notice here? I'm going from what? Negative 2 to what? 2. So won't it be worth my time perhaps to see if this has any type of symmetry, which might make the integration a little bit or a lot easier? Yes? Okay, so real quick. So if this is my function, how do I test for symmetry algebraically? What do I do without graphing? I what? Yeah, put in negative x for x and then play around with it and see what happens. Okay. All right, well that stays there. Now what did you just learn or relearn a few minutes ago? When you run into sine of negative x, you can replace it with what? What can you replace sine of negative x with, guys? Can't you replace sine of negative x with negative sine x? And by the way, if you want, you can pull out the negative. Okay, so look what happened, guys. When you replaced x with negative x, and you compare that to that, how do those compare? Are they the same? No. So it doesn't have y-axis symmetry. Are they complete opposites? Yes, which means it has what? Origin symmetry. So if the function has origin symmetry and you're integrating from negative a to positive a, what's the value of this integral without doing any calculus? 0. Because an origin symmetry function will have something like this, for example, where the positive and negative area add up to 0, don't they? So didn't that save us a ton of work, didn't it? By a quick symmetry test? Okay, everybody do the next one. getting warm in here, or is it just me? It's getting warm? No? All right, anyway. Okay, shh, guys, so the only time it might even be worth your while to check for symmetry is when? When these are what? Yeah, opposites, right? Otherwise, symmetry won't do you any good, right? So when those are opposites, it might be worth a few minutes to check for symmetry. Ready? Okay, so doing that, how do I check for symmetry without graphing? Replace x with what? Negative x, and then play around with it. Okay, so with that in mind, if I simplify, I get this. If I simplify this, I get this. And now, when you compare f of x with f of negative x, they're the same function, aren't they? Which means this has what? What type of symmetry? Yeah, it's y-axis symmetry. It's an even function, right? By the way, this one's odd, but whatever. And so with that in mind, what that means is you can what? Integrate from what? 0 to what? 3. And then what? And then when you're done, just make sure you double your answer by multiplying it by what? 2. And then you could finish it pretty easily from there. Okay, so again, this isn't going to save me a ton of work, but it will save me a little bit of trouble at the end. I won't have to stick in a -3 and all that. Does that make sense? Yes? Okay, but you still have to integrate to get the answer there. All right, so that's it. Let me stop this.